Hello everyone, my name is Alan from the Hong Kong Polytechnic University. This is a video presentation of the paper An Optical Communications Perspective on Machine Learning Applications in Journal of Lightwave Technology. Article authors are Dr. Faisal Khan, Qi Fan, and also my colleague Professor Chao Lu. The machine learning has seen a lot of applications in our community of optical communications in the past few years. So we are hoping that we can take this opportunity to share with our friends about some basic principles of machine learning and how we think machine learning can be applied and play a role in optical communications and networks. So what is machine learning? To put it very simply, oversimply, I would say, it is to train computers and machines to learn patterns from data without being explicitly programmed them to do so. Okay, so it is fundamentally about pattern recognition. And realistically, what they are doing is they typically are involved in two types of tasks. The first one is called classification. So you have sets of data, and you classify them into different sets or labels. Okay, and then another type of pattern recognition is what we call regression. Okay, you can find some simpler descriptions of the trends, and then you can use the trends to do some predictions in your respective application. Machine learning algorithms tend to perform exceptionally well even when the underlying physics or mathematics of the problem cannot be described explicitly. It is actually exactly because of the fact that it can perform really well when we cannot have a better analytical understanding of the problem concerned. That makes machine learning so powerful. Now, why is machine learning hot again these few years? So we think there are quite a few reasons. Now, first of all, we have much better computational power than 10 years or 200 years ago. Second, we have a flood of a lot of data in various disciplines because we have 2 decades at least of internet. We also have growing progress on the machine learning algorithms itself and also the related theories. And there has been increasing support from industries. So these few years, the newer advance is what we collectively call as deep learning. Okay, so basically that is to learn multiple levels of representations, or graphically we call it deeper neural networks. Is one of the examples. And what's amazing is that these deep learning techniques actually produce amazing performance improvements. A lot of them actually beat a lot of human level performance, and this is why deep learning becomes very popular again in the past few years. So now you don't have to be an expert in technology discipline to understand that machine learning seems to be applied to everywhere in all parts of the society, from image processing, bio-related, computer visions, and also business-related activities. Now, how is machine learning related to communications? Now, in our world of communications, we actually do classifications and regressions all the time. Now, for example, on the left, we actually do classifications such as symbol detection. So this is a QPSK signal distribution, and then we have decision boundaries, which classify them into 4 classes. Okay. For regression, we also do this all the time. The graph on the bottom right is the plot of the received signal phase raised to the 4th power. And what we do usually is we estimate the slope and the intercept, and then we call this carrier phase and frequency offset estimation. So we do these 2 tasks all the time, but we just don't use this terminology. Now, how about linear systems in general with memory? So in this case, we also do a lot of difficult or complicated signal processing to try to recover the symbol X from the observed Y. Okay, and then we know this thing called maximum likelihood sequence detection. So we have all the formulas to show whatever we have done is the optimal. So, and we actually have this since in the 60s. So what we want to say here is that for linear systems, there's actually no need or no place for a lot of these current very complex machine learning techniques such as recurrent neural networks or long short-term memory networks or anything that fancy. Okay? There's essentially no place for machine learning for linear systems, right? Or more generally, for systems that we can explicitly statistically characterize the input and outputs. Okay, so in communications, what are, or in optical communications more specifically, what are machine learning's role? So we think that there are a few areas in which machine learning can have an impact in optical communications and networks. The first one is fiber nonlinear compensation. The second one is what we call optical performance monitoring. And the third one is more network related, is proactive fault detection and prevention of network components. And lastly, impairment aware software defined networking, which is also one of the hottest things in the networking area. So the purpose of the invited paper is to try to provide a tutorial based on basic machine learning techniques from a communications point of view, or trying to use some of the jargons that we are more comfortable with. Okay, and then we will talk about how these techniques are applied in the areas in communications and networking that we have just mentioned. Now, we would like to make a disclaimer here. Now, this paper is definitely not a comprehensive overview of the current state-of-the-art machine learning research and their challenges. Far from it, in fact. Okay. Also, it is not the only way to understand machine learning. Right? We are just trying to provide a way that we think it's a bit closer to how we understand communication systems. And so we will proceed to talk a bit about some basic machine learning techniques, such as artificial neural networks, support vector machines, some clustering techniques, and then some introduction to the more recent deep learning. And then we'll talk about how these techniques are applied in the 4 areas in optical communication networks. We will then also talk about some observation and trends and the outlook of this field of machine learning in optical communications and networks. Okay, let's start from the very basic machine learning techniques on artificial neural networks and support vector machines. Now, let's start with something even more fundamental. What are the kind of classification problems that would need neural networks? Now, suppose I have a data set of 2 classes, the green one and the purple one, right, in this 2-dimensional representation. Now, for these sort of example, you actually do not need a neural network to do classification, because the decision boundaries is quite simple and obvious. Now, suppose this is what your data set looks like. For this case, you still do not need any neural networks, because the way to do decisions is simply this line. And mathematically, what you do is you actually take the input coordinates, and then you will do a transformation, a rotation, characterized by this W here, okay, and then this B here would correspond to a translation, okay, and then you can do a decision that way. So you rotate this thing back to X or Y, and then you do decision. Okay, so this is still something that's simple enough that you do not need machine learning. Now, and then the decision, we call this activation function in the machine learning community, which is basically a nonlinear function. So now, suppose your dataset looks like this. Okay. Now, so what you do in this case is that you will first, okay, take the input coordinates, and then you do a red line decision boundaries, okay, and then you do a decision boundaries based on this blue line, and then based on the decision outputs of these 2 decision functions, you find that this is the right region for you to classify the green data. And then so what you do is you actually pass the decision outputs into another decision function. Okay, so in this case, that actually is the simplest kind of artificial neural network. So what we want to show here is that fundamentally your data set needs to at least look like this, right, in order for us to warrant the use of some sort of machine learning. All right, so let's talk about artificial neural network in a bit more detail. Okay, so basically we start with a certain set of input-output pairs. Okay, the X is the input, the Y is the output. Okay, now so we for this example we can think of the input as, for example, images. Okay, and then the output here is to categorize whether it is an image of a cat or image of a dog. Okay, so here's your input, okay, and then you put it into a neural network, where it basically contains the input layer, okay, and then there will be an operation W X times B, and then there it's typically activation function, a nonlinear function, okay, and then this bunch of nodes, okay, we call this the hidden layer, okay, and then the hidden layer continue to have another linear transformation, and then followed by some nonlinear function, okay, and you have the output here, and the output typically you want it to be as close to the target, or the output data Y, or they call it label, as much as possible. Okay, so in these are examples, typically the way we label the data is, for example, if it is a dog, then the output is a 1×2 vector, okay, with this form, and then if it's a cat, the output looks like this. Okay, so the way we label this output, the term for it in the machine learning community is called one-hot encoding. Okay, now in communications, you can kind of think of this as some sort of frequency shift keying kind of format, okay, where each class belongs to one particular slot in the output dimension. Okay. All right, now so let's look at the ANN structure a bit more closely. Okay, so typically, again, we have the input layer and the output layer. Okay, and then there is a hidden layer, and so there's this thing called hyperparameters. Basically, it is the number of hidden layers and the number of nodes each layer. Okay, so when we talk about number of nodes, okay, so for example, for the input layer, the number of nodes is more or less fixed. Okay, so it's the size of your input, whether it's an image or a vector, whatever you have. Okay, the output, okay, sometimes it is determined by the number of class that your data has. Okay, so the number of nodes at the input and output is relatively a bit more straightforward, because there are some reasons, some logic behind how you choose the number of nodes. Okay. The hidden layer, on the other hand, there's actually no particular logic or formula to dictate what is the number of nodes required. And also, by the same discussion and argument, there's also no particular formula to show you how many hidden layers are required for a problem. Okay, so these are the hyperparameters. The choice of these hyperparameters becomes something more from an experience point of view. It becomes the sort of art of machine learning researchers. Like when you are in this field long enough, you have a feel of how many hidden layers or how many nodes should be more appropriate. Okay, the important point here that we want to highlight is that there is no hard rule on the choice of all these hyperparameters. Okay, and so then typically, now one example of how we try to find the right parameters, W and B here, is that we wanted to find these parameters W and B, okay, to minimize, for example, the mean square error between the label and the output. Okay, so this is something that we are quite familiar with as communication researchers. Okay, so we try to minimize MSE all the time. So here the spirit is the same. The problem is to try to find the W and B parameters to minimize the MSE between the neural network output and the presumed output label. So the objective again is to find the parameter values, the W and B's, that minimize the cost function. Now, like all other fields of science and engineering, when we try to minimize something, a lot of the times, practically, what we do is we do gradient descent. Okay, so we will have a set of parameters, theta. Okay, and then the way we try to find the optimal values is through gradient descent. Okay, so basically the new update is the old one, and then minus the gradient times essentially learning factor alpha, okay, a scaling factor, or we call step size. Okay, so and sometimes we actually have this thing called mini batch in the literature. Basically, what mini batch means is that at each iteration step, we actually use more than one data point to update our estimate. So in this case, for each update, okay, we would use more than multiple points to update our values. Okay, so and then also the way it works is we'll typically update the parameters closer to the output first, and then followed by the ones that is closer and closer to the input. Okay, so in this case we'll update the W2 B2 first, followed by the W1 B1. Okay, and so this is why this algorithm is called backpropagation. Okay, so the updates first start towards the end of the neural network, and then the update will continue to propagate back in the neural network, and then the parameters closer to the input will be updated the last. Okay, so that's why it's called backpropagation. And so the paper will have the detailed derivations of these update equations. Now, let's talk a little bit about the activation functions, or the nonlinear functions that we use at hidden nodes and also at the output layer. So remember, in terms of classifications, one way to understand these nonlinear functions is they are essentially decision functions. Okay, so therefore, some common choice of the activation functions are, for example, sigmoid, okay, and also a hyperbolic tangent. Okay, so you can see from the graph here that these two functions actually quite resembles decision functions. Now, however, when it comes to the practical implementation, people start to find that these sort of functional shape sometimes get into this problem of what we call vanishing gradients. So what that means is, if you are currently at here or at here, for example, your gradient actually will be quite small. So what that means is your parameter update will be quite slow, and sometimes the algorithm got stuck. Okay, so in response to that, these days one of the so-called newer activation function which becomes quite popular is what we call the rectified linear unit, or ReLU. Okay, so what that means is basically when it is smaller than 0, the output is a flat 0. When it is bigger than 0, the output is a linear function. So in that case, it sort of kind of achieve balance between the fact that it needs to be some nonlinear function, and also that the parameter updates will be less likely to undergo these vanishing gradient problems. Now, another important class of activation function is what we call the softmax. Okay, the softmax, basically what it does is you have an input vector, okay, and it normalizes itself so that the softmax output is a valid probability distribution. So this is typically used at the output layer of a neural network. Okay, another on cost functions. So we have just discussed about the MSE as a common cost function. So this is essentially the same spirit as a lot of communications-based problems. Okay, now another class of cost functions that is used quite often in machine learning is what we call cross entropy. Okay, and it can be shown that the cross entropy basically is expression relating the original label, output label, and the output of the neural network. Okay, so this expression, it can be shown in our paper that this essentially is the KL divergence between the distribution Y and O. Okay, so therefore, that's partly why for problems that use cross entropy, the output vector O needs to be a valid probability distribution. Okay, so if you see that way, at least we can sort of appreciate that this cross entropy is kind of a measure between the similarity between two probability distributions. So it kind of makes sense as a cost function to optimize. In the machine learning community, we also call this the loss function. So typically, in regression problems for neural networks, okay, we will use the MSE as a cost function, okay, and the output layer here typically has a linear output, so meaning no activation function for the very last layer, okay. For classification problems, typically we use the cross entropy as a cost function, and the last layer typically is a softmax layer. All right, now when you have a set of training data, you can actually train the ANN so well that it fits perfectly with the result you want. Now, actually, this is a case where it is not that meaningful, because for most applications, what you want to do is you use some training data and then you learn a model, and the model will be able to perform well on another set of independent data we call testing data. So this is typically what we wanted to do in most applications. So in this case, it is easy for the ANN to be what we call the overfit if we only care about its performance in the training data. Now, on the other hand, you have this thing called underfitting. In this case, it can be caused by a lot of different issues. For example, insufficient training time, number of iterations, the number of hidden layers is not sufficient, the number of hidden neurons is not sufficient. Collectively, what it does is your trained model is too simple for the data that you have at hand. So therefore, in training ANN, what we typically do is we want to achieve a balance between these two scenarios of overfitting and underfitting. So typically, we have this thing called a validation set, which is used during the training process. So you have a set of training data, and then when the neural network is learning its parameters in regular intervals, it tries to use the validation data set to test the performance of the trained neural net at that moment. So in that case, during training, there's still a sense of an independent set of data for testing. So in that case, typically it can help to achieve a balance between overfit and underfit. Now, another class of machine learning techniques that we will talk about is support vector machine. Now, consider this example of two classes of data, and the data are two-dimensional, x1, x2. Now you can see here that the decision boundaries should look like a circle. Now in this case, what support vector machine does is it transforms the data from the original variable space to what we call a feature space, so that it can do simpler decision boundaries. Now this is an example. So for example, we can do this transformation from x to v, okay, so that you have one new variable, v3, which is basically the radius square of the data. So in that case, when you look at the data in the V space, the decision boundaries is a very simple plane at V3 equals 9. Okay, so basically that's the essence of support vector machine. So again, the idea is to transform the data from the original variable space to typically more high-dimensional feature space, so that in this feature space, the decision boundaries are pretty straightforward, or geometrically, it will look like plane decision boundaries. Okay, so when it translates into the a bit more detailed mathematics, what that means is that when you transform it to the V space, the feature space, you would want to find what we call an optimal hyperplane here, okay, that best separate the two classes of data. Okay, so now in more detailed terms, what do we mean by finding the optimal hyperplane? So what that means is that if given the data, once we transform into the feature space, okay, now if you look at the red and blue data here, so graphically you would want to put a plane, okay, the orange line to be in the middle of these two clusters of data. Okay, so more particularly, you would want to put it in a place so that it maximizes the what we call the margin D here. Okay, so now in this example, the margin D, okay, it's the projection of this vector vi minus v plus on this vector w. Okay, all right. So therefore, the margin, okay, is given by this expression here. Okay, the angle cosine phi, naturally it can be written in this way. Okay, and so put in the algebra. So the paper will demonstrate the algebraic details, and so what we will show is that the margin eventually, okay, has this expression is 1 over the magnitude of w, so where w is the parameter that describes the orientation of the hyperplane. Okay, so in our support vector machine optimization, what we are essentially doing is we would want to find the w and also the offset b here that maximize this margin. Okay, all right, and so now that optimization procedure is actually rather standard. So in this day and age, once you formulate optimization problem, and then you will have a lot of standard numerical algorithms to help you to solve for this optimization problem. And so rather, one of the other things that we wanted to highlight is how do we transform the data from the original space X to the feature space V. Okay, so typically it is done through a kernel function. Now, so supposedly we would want to find a good transformation, okay, characterized by this function here. All right, now but typically what happens is we look at it together. Okay, so we would look at a more general kernel function that takes in two data from the input variable space. Okay, then the outputs number that actually represents how it is transformed. Now, typical kernel functions that we use Sometimes we use polynomial. Sometimes, actually, a lot of times we actually use what we call the Gaussian radial basis. Okay. Also, sometimes hyperbolic tangent is used. Now, unfortunately, there's not a lot of more fundamental arguments or suggestions on which sort of kernel functions you should use for whatever scenarios, because this a lot of times it actually comes from experience when it comes to choosing the right kind of kernel functions. All right. So, and I would like to take this chance to try to put things in perspective. Now, we have talked about ANN and SVM. Okay, so to us, one way to see the relations between these two things is that the ANN, okay, you can think of it as you have some input, you have some set of data, okay, and then the task is to find the right decision boundaries, okay, and no matter how complex it is, okay, so you can end up with very curvy and weird decision boundaries. That's essentially what the ANN is doing. Now for SVM, in a way it is doing something in another direction. So what it does is, instead of finding complicated decision boundaries, it actually transforms the original problem, the original problem into a new problem in a new variable space. We call it feature space, so that in this new feature space, the classification is actually very simple. It actually just looks like a simple straight decision boundaries. So it's in that sense that these ANN and SVM are in a way complementary. Okay, now for all the examples you have described up to now, the data consists of input-output pairs, meaning I have an input, it can be an image, it can be a piece of music, whatever. The output is certain class labels, like a picture of a dog or a cat. Okay, and then you want to build a neural network so that when you have an input, the output best match the intended output that you have. So this is called supervised learning, when you have an input and output pair, and the output pair typically we call it class label. Now there are another class of problems in which there is no pre-labeled output class. Okay, so for these sort of problems, we call this unsupervised learning. Okay, and the idea here is to try to find the hidden patterns all by the algorithm itself without knowing the class label beforehand. Now I'll give you one graphical example. Right, so for example, you have a class of data. Okay, so you can see visually that the data kind of more or less should belong to three classes, right? Because it seems like there are three clusters. Okay, but then we actually do not have the class label for each data point. Okay, so for a human, we don't need it for this example because it seems it's quite clear to our eyes that these set of data probably belongs to three different classes. Okay, and so this sort of problem we call unsupervised learning. Okay, let's talk about one example of unsupervised learning, so clustering. Okay, so this is called k-means clustering. So what it means is the following. So let's say you are given input data. Okay, so visually you know that it seems that there should be two classes. So then you just initialize the location of the center of these two classes randomly. Okay, so let's say I have this red and blue centers of the two classes. Okay, and then what you do is you just map the points that are closer to the red center as the red points. Okay, the points that are closer to the blue center as blue points. So you see this is sort of like how the points are divided. Okay, now then afterwards, based on the class of the points at that moment, you recalculate the center of the class Okay, and so now the center is here. Okay, then with the new center, you then recategorize or reclassify the points based on whether the data points are closer to the red center and the blue center. So then this is what will happen afterwards. Okay, and then so by now you will see that in a way the algorithm has converged. Okay, you can recalculate the center based on this classification, which is around here and here. Right? So then at this moment it sort of agrees with our intuitive explanation. So this is what we call k-means clustering. Okay, so it's an iterative algorithm. Now, whatever I said just now, if you translate it to mathematics, that will be these two formulas reiterated with each other. Right? So basically, it is calculating, determining the class of the data, and then based on the class, you calculate the center of the class. Okay, and then you do it iteratively. Okay, so this is called k-means clustering. Now here it's a more generalized version of k-means clustering. We call this expectation maximization algorithm. Okay, so what it does is not only do they estimate the means of the class, it also estimate the covariance. Okay, and it do that in a more what we call soft manner. Okay, so what it means is the following. So again, same data set, you can initialize the location, and also now the circle here means the initial covariance, right? Which is initially we set it to be a circularly symmetric sort of covariance covariance matrix. Okay, so then afterwards, when you try to assign each data point to the class of red or class of blue, okay, we don't really do a hard decision. So we actually have a weighting factor. Okay, so it's a probability of whether a particular data point belonging to a particular class. Okay, so each class has a posterior distribution of which class. So each data point has a posterior distribution of which class it belongs to. Okay, so therefore you will see some gradients of the colors here. Okay, so then in that case, once each data point has a certain distribution of the class assignment, then all the means and variance are calculated with a weighted average. Okay, so the mean here is a weighted average of the class label. Okay, and also the covariance matrix. It's the empirical covariance, but then weighted by whether that particular data point belongs more to one class over the other. Okay. Now here is another type of unsupervised learning techniques that has to do with what we call dimensionality reduction. Now suppose you have a set of data, three-dimensional data. Okay, you can see here graphically that the data seems to lie in a lower dimensional space. So for a lot of applications, it is necessary and very beneficial to identify these lower dimensions so that we can carry on with whatever task that we are dealing with. And so the technique of what we call principal component analysis is to try to identify these lower dimensions based on the data. Okay, so more specifically, if you have a set of data X, okay, so what you do is you first calculate the empirical covariance, okay, and so once you have that covariance matrix, what you do is you will look at the eigenvectors and the eigenvalues of these covariance matrix. Okay, so the point here is to try to identify or find the few eigenvectors with large magnitude, and we call this principal components. Now the way to understand it is to say the eigenvectors basically decompose the matrix into another set of orthogonal bases. Okay, and large eigenvalues essentially here actually means large variance. Okay, so finding the eigenvectors that has large eigenvalues essentially is equivalent to finding directions in the original space that has large variance. Okay? And so so it, that basically means we are trying to find the particular subspace that covers a lot of data points. Okay, so the result here for this uh, graphical example is that you'll be able to identify the first two eigenvectors, essentially a plane that pretty much capture most of the dynamics of the data. So that is called principal component analysis. All right. Um, Reinforcement learning is yet another type of machine learning techniques. So this is not supervised learning. This is not unsupervised learning. Now, reinforcement learning has to do with an environment, okay, such as a video game, okay, in which you have observations, you have the state of the environment, and then what you do is you try to take actions, and the objective is to optimize some sort of reward. And so, for example, in a video game setting, your reward may be you get past all the hurdles, go to the next stage, and win. Okay, so the idea here is that you are given the video game as an example, okay, the observation. You play the video game, you take your actions, and then eventually you want to optimize your reward. Okay, so in a lot of examples of reinforcement learning, what you will see is you can start off with a system that actually knows nothing about the environment. For example, we can start an algorithm that doesn't even know that walking to the right is the right thing to do. Okay, now after reinforcement learning, you can actually train the computer to actually beat the game in a way that is much better than any human can. Okay, so this video clip is taken from a demonstration called MAR.io, which you can find on YouTube. Okay, so in a lot of examples of reinforcement learning, it is difficult to analytically, explicitly uh, express the reward as a function of observation and actions. And that is partly why some of these reinforcement learning techniques are so powerful and amazing. So now, is reinforcement learning applicable in optical communications? Now, I'm just going to give you one example to illustrate the point here. One example is actually the constant modulus algorithm that I believe all of us are familiar with. Okay, so the idea is you have some sort of cost function. Okay, now in this case it is the distance between your output and the prescribed circle radius of the signal power. Okay, your input is the filter taps. Okay, so in the CMA we try to find the filter taps that minimize this cost function. Okay, and we can take the derivative, the stochastic gradient descent, and then you have all these update equations. Okay, so now this is actually an example of reinforcement learning. Okay, so we are trying to optimize an objective function. Okay, all right, and so we do it in an iterative way. So this is technically reinforcement learning. Okay, but the more important point here is that in our community we just simply call them adaptive signal processing. Okay, so this is because in the physical layer communications, most of our problems, it can be, the cost function can be explicitly written as a function of the input variables, okay? And it is differentiable. Okay, so for these sort of scenarios where you can actually write down a detailed equation, we don't really call them reinforcement learning, we just call them adaptive signal processing. Now there are some applications of reinforcement learning in more network layer, self-configuration and resource allocation sort of problems, which we will go through in the paper. Now it comes to deep neural nets, okay, deep learning in general. Okay, so one major difference between conventional neural nets and what we call the deep neural nets is that the architecture has a lot more layers. Okay, it's much deeper in a way. Okay, so this is one graphical example. Okay, so it can also have a lot of different types of features, such as a feedback and memory within the neural net architecture, and this is something that we'll go through briefly. So perhaps one conceptual difference that we can understand between conventional neural nets and deep neural networks is the ability to identify features itself. Now, what do I mean by that? So let's take OSNR monitoring as an example. Okay, so in conventional neural nets, typically what we do is we receive our signal, and then we typically feed the samples or the signals at the pulse center, put it as an input of the neural net, and then we hope the neural net can give us the correct OSNR values. Okay. In deep neural nets, if you have a lot more layers, so it turns out for some applications you can just feed the whole image, right, into the deep neural net. Okay, and then the deep neural net will be able to somehow extract the right features, and then they will be able to give you a good OSNR estimate. So conceptually, the difference here is that the conventional machine learning, okay, you have to first participate in picking the right most relevant features for your problem. Okay, in deep learning, actually, you can think of it as the neural network itself automatically will be able to pick the best features. Okay, so it is in a sense that the deep neural net seems to be more intelligent. Now, what's more interesting or fascinating in some applications is that the deep neural net actually were able to provide superhuman performance. And then when you look deeper into what they are doing, it turns out that sometimes they pick out features that actually humans did not see. So in a way, they discover new things that is beyond what the level of understanding of humans. And so that's partly why these deep neural nets become so fascinating in certain areas of science and engineering. So now, because the deep neural networks has a lot of hidden layers, it can have a lot of nodes per hidden layer. Okay, so when it comes to training the deep neural nets, you would imagine that there is a lot of additional issues. Okay, so stuff such as vanishing gradients that we briefly mentioned, it becomes even bigger problem. Okay, and then different layers can learn at different speed. Okay, too many parameters to learn, etc., etc. Okay, so these are more problems in the actual learning algorithm itself, on the how you update the parameters. Okay, so we'll just talk about one particular approach. Okay, so there's this approach called autoencoders, in which case what they do is they train the network layer by layer. Okay, so they train the hidden layer 1 first. Okay, the way they train it is, in a way, you transform the data using the hidden layer, and then you try to ensure that the data here can be somehow retransformed back to the original signal. So when you have that, then you can consider layer 1 is trained. Then you move on to layer 2, okay, and then you do the same thing. Okay, so it's like, you can think of it as compression and decompression. Okay, so you transform to another set of nodes, and then as long as you can recover the original one, okay, from the transformed one, okay, then you consider this layer to be trained. Okay, so now because we are the consumers of these deep neural nets, so we felt that let's not spend a lot of time to talk about the detailed new algorithms or training, because so this actually is a major area of machine learning research. But for us, I think we are the consumers. Okay, so let's just appreciate that there's a lot of work that is happening in this particular area. Okay, one of the common type of deep neural nets is what we call convolutional neural networks. So convolutional neural networks are typically used for pattern recognition within images, but not limited to that, but typically. Okay, so the basic structure consists of the following. You typically will have an input, let's say it's an image, okay, and then it will pass into interleaving layers called a convolutional layer and also a pooling layer. At the end, we have what we call a fully connected layer. Okay, so the features of the convolutional layers is that it actually use shared weights. Okay, so now this is a graphical illustration of one particular layer of a convolutional layer. So the color of the connections here actually denotes they are connections with the same weights. Okay, so this is one feature of the convolutional layer. The pooling layer basically typically just picks the largest value within a neighborhood. Okay, so for example, this is if you are talking about picking the biggest number within this neighborhood, then the biggest number is 5 here, so this is called pooling, okay, or max pooling to be exact. All right, and so at the end, towards the end, the fully connected layer, actually that's just similar to regular ANN, and the purpose typically is to map whatever you have to the final output. So now here's how we can try to interpret what the CNN is doing from a more telecom perspective. In fact, when people say the weights of the convolutional neural network of the convolutional layer is shared, what that means is, from a telecom point of view, this is rather simple. That actually just means that the convolutional layers are actually correlators. Okay, and why do they call it convolutional layer? That's because this operation from one input to the next layer with shared weights, that actually is the same as convolving the original signal, two-dimensional signal, with another two-dimensional signal. That is the weights. Okay, so that is 100% within what we understand as in linear systems. Okay, so now what that does overall is that the convolutional layer basically are trying to correlate this image and see whether this image is present in the original input. Okay, so in a way that this is trying to identify or locate, okay, this image feature within the bigger image. Okay, so this is what the convolutional layer is essentially doing, locating specific features in the image. Okay, so the pooling layers basically is like some sort of downsampling where you pick the place where that the feature is the most prominent, okay, and also reduce the dimensionality of the what we call the feature maps, right, the group of features. Okay, so now if you see it this way, then the interleaving convolutional layer and the pooling layer basically is like they're trying to extract bigger and bigger features from the input to the output. Okay, and this is also why sometimes we can interpret what the neural network is doing by looking at the features. Where sometimes when people are trying to extract determine whether an image is a dog or a cat, and then if they look into the details of the convolutional layer, they discovered that the learning algorithm actually tries to learn specific features of the dog's face and cat's face, and this is how one can try to interpret what the neural network is doing. Now, I wanted to make a statement or word of caution uh, on this particular aspect of explaining what the neural network is doing. Okay, sometimes we are able to look into details and understand what the neural network is doing. Sometimes we cannot. Okay, and the fact that we cannot understand why what it's doing doesn't mean it is not doing well. A lot of times, the neural network performs really well, and then people can never really understand how exactly it works. Another type of deep neural networks is called recurrent neural networks, or RNN. Now, these are typically used for data sets with some relations to each other, or you can say with memory. Okay, for example, speech data, or in our community, telecommunications, you can consider signals affected by intersymbol interference (ISI) as an example of data sets with memory. Okay, so one um, example of RNN is shown here. Okay, so essentially you have input, output. Okay, and then the weights is similar to ANN, and then there's a hidden layer. Okay, now what's extra is this feedback connection. Okay, that feeds itself back to data at t+1. Okay, so you can unfold this in time, and then it can look more or less like this. Okay, so the output, okay, depends on the hidden layer, but the hidden layer itself also depends on its value at t-1. Okay, so this is essentially what simplest RNN is about. Now, if you actually take off the nonlinear term here, okay, if you take off the sigma 1, sigma 2 here, okay, so this will become a simple linear channel with memory 1. Okay, so essentially what the RNN does here, it's when you train the RNN, okay, you are trying to learn the memory structure through the input-output data. Okay, so you can think of it that way. So the concept of learning the model is essentially the same as ANN, okay? But then in this case, the backpropagation, we call it backpropagation through time, okay? So the derivation is slightly more complicated. The paper will have the detailed derivation. So you can see that in this example, the memory length or depth, okay, if you use telecom jargon, is just 1. Okay, so you can imagine that this concept can be extended, okay, to what systems with larger memory length. Okay, and so in the machine learning community, the one step forward on that is what we call long short-term memory, LSTM. Okay, so this actually it's an extension of this idea to try to learn some long-term dependencies in data. Okay, so now I want to take this chance to provide one example of RNN applications and to contrast that with what we have in telecom. One typical applications of RNN is natural language processing. Okay, so what does that mean? Let's just take machine translation as an example. It's one of the hottest areas in machine learning right now. So the idea is to input a sentence in one language and convert to another language. Okay, so for example, this is an example of translating Chinese into English. Okay, so knowledge is power. Okay, so in this example, what happens is that you can actually translate everything quite literally. Okay, so the first 2 characters of the Chinese correspond to knowledge, and then the last 2 characters correspond to power. So that is pretty literal and simple translation. Now compare that with another example. Okay, this is a slightly more elaborate translation. Okay, the point that I'm trying to make here is that in this case, because of the linguistics difference between Chinese and English, you do not directly translate every character literally. Right? So, for example, in this example, the compensate actually kind of comes from these two characters. Okay, intellect is here. Okay, uh, extremely is here. Okay, well read is kind of here. It's not even a very good direct translation between this particular character. Now, the reason why I want to talk about this is I want you to appreciate the difficulty of this problem of translation and why it needs RNN, and compare that with the problems that we have or we deal with in telecom. Okay, so if you think about this problem in more abstract terms, or if you want to think about this problem in more telecom language, now what this is doing is this is trying to learn some data dependent nonlinear memory structure. Okay, so the translation actually depends on the exact content of the words. Okay, and then so therefore this memory structure actually is data dependent, and then you have to do it adaptively. Okay, so this is the kind of difficulty of the problem that RNN typically deals with. And so I want you to contrast that with the kind of problems that we deal with in telecommunications. I don't think we have a problem that complex. Okay, so we have we learn about the memory of our channels. Okay, the memory structure typically are not dependent on the input signals. Okay, so yeah, so this is I just want to give you a comparison of the kind of problems that we deal with in telecom and what machine learning researchers are dealing with using RNN.
Now, over the past few years, machine learning has been applied in various aspects of optical communications and networking. In this paper, we have mainly focused on the application of machine learning algorithms in solving problems which are mainly related to the physical layer of an optical network. These include nonlinearity compensation, optical performance monitoring, proactive fault detection and preventive maintenance, and cross-layer optimization in software-defined networks. In this paper, we made use of a simple single hidden layer neural network for nonlinearity compensation in a digital coherent receiver, and we applied a training technique called extreme learning machine. Now, during the training phase of this neural network, the I and Q components of the received symbols after CD compensation are applied at the input of the neural network, while the actual signal phase are used as the targets. And then this neural network learns the mapping between the input and the output parameters. Now, the advantage of this simple structure is that it has faster training as well as lower computational complexity. Next, we use the trained neural network for nonlinearity compensation for RZQPSK signals, which were transmitted over 2000 km standard single mode fiber. Our results demonstrate that the neural network-based nonlinearity compensation technique demonstrates comparable performance to digital backpropagation technique, while its computational complexity is much lower as compared to backpropagation method. Apart from artificial neural networks, other supervised and unsupervised machine learning techniques have also been used for nonlinearity compensation in optical networks. For example, for dispersion managed systems, Lee et al. Demonstrated the use of SVMs for nonlinearity compensation. In their work, they make use of SVMs to determine the optimal nonlinear decision boundaries. Their results show that this approach demonstrates better performance than conventional nonlinearity compensation methods. However, one of the issues with this approach is that since SVMs are binary classifiers, therefore the detection of MQM signals would require the use of multiple SVMs in that case. Similarly, for dispersion managed systems, Zibar et al. Have shown the use of unsupervised machine learning techniques such as expectation maximization and k-means algorithms for nonlinearity compensation. In their work, they make use of these algorithms to determine the optimal nonlinear decision boundaries. Their results also show a 3 dB improvement in nonlinearity tolerance. On the other hand, for dispersion unmanaged system, this approach provides minimal performance gain because the optimal decision boundaries in that case would be nearly straight lines. Machine learning techniques can also be used in combination with existing DSP strategies and analytical models for nonlinearity compensation. In this context, Hager et al. Have shown that the interleaved linear and nonlinear operations in standard digital backpropagation algorithm uh, can be modeled by using a deep neural network structure. Here the matrix W represents the linear CD operations, while this function sigma represents nonlinear phase rotation. The loss function of this deep neural network is differentiable with respect to the real and imaginary parts of W and sigma. Therefore, we can make use of backpropagation algorithm to learn all the parameters in W as well as nonlinear functions parameter. Their results demonstrate that this learned digital backpropagation algorithm's performance is similar to that of standard digital backpropagation algorithm. However, its computational complexity is much lower than that of standard digital backpropagation algorithm. Another important area where machine learning techniques have been applied extensively over the past few years is optical performance monitoring in fiber optic networks. We know that fiber optic communication networks are becoming more complex, transparent, and dynamic in nature. The reliable and efficient operation of these networks require real-time information about the quality of various physical links in the network. Now, optical performance monitoring is basically a set of measurements which we perform on an optical signal in order to estimate various physical parameters of an optical channel. These parameters may include, for example, different impairments such as CD, PMD, PDL, etc., as well as other useful parameters such as optical power and optical signal to noise ratio. OPM can enable several useful functionalities in optical networks. For example, it can be used for adaptive impairments compensation. More recently, OPM techniques have been used for impairments-aware routing as well as other useful functionalities in software-defined networks. Machine learning techniques have been considered for low-cost multi-impairment monitoring in optical networks. In this paper, we demonstrated the use of an artificial neural network in combination with empirical moments of received signal amplitude distributions for the joint estimation of OSNR, CD, and PMD. We have shown that the empirical moments of received signal amplitude distributions are sensitive to CD, OSNR, and DJD. The impairments dependent patterns reflected by these parameters can be exploited by using ANN based pattern recognition for the joint estimation of these parameters. So in our approach, we apply the empirical moments of received signals as input features to an artificial neural network, while the actual known impairments values corresponding to these empirical moments are used as targets. And then this ANN is trained to learn the mapping between these input features and the target. After the training, the ANN is able to predict the unknown impairments values of received signals. Our results demonstrate that this technique can enable joint OSNR, SINE, CD, and PMD monitoring with good accuracies. This plot shows our OSNR estimation results for different modulation formats and data rates. As we can see that the OSNR estimates are quite accurate. Since this technique uses extremely simple hardware, it is attractive for low-cost ubiquitous deployment in fiber optic networks. It is difficult to realize such low-cost multi-impairment monitoring by relying only on physical modeling. Apart from conventional machine learning techniques, deep learning technologies have also been considered for optical performance monitoring. particularly for OSNR monitoring in fiber optic networks. The rationale behind the use of deep learning techniques is that instead of using human-crafted features, these techniques can enable OSNR monitoring without involving any manual feature engineering. In this paper, we demonstrated the use of a deep neural network in combination with amplitude histograms in a digital coherent receiver for OSNR monitoring. Various layers in these deep neural networks are used for the automatic extraction of OSNR sensitive features of amplitude histograms, which are subsequently exploited by DNN for OSNR monitoring purpose. Similarly, Tanimura et al. Have demonstrated the use of a convolutional neural network in combination with asynchronously sampled raw data in a digital coherent receiver for OSNR monitoring. Various convolutional and pooling layers in the CNN are used for automatic extraction of OSNR-dependent features of asynchronously sampled raw data, which are eventually used by the CNN for OSNR estimation purposes. Another interesting work is demonstrated by Wang et al. In their work, they treat the eye diagrams as simple images, and then a convolutional neural network is used for the automatic extraction of OSNR sensitive features of these eye diagrams, which are subsequently used by the CNN for OSNR estimation purposes. Now, all these three techniques have demonstrated OSNR monitoring for various modulation formats and data rates with good accuracies. One big advantage of these deep learning based approaches is that they can enable OSNR estimation without involving any manual feature engineering. One problem commonly encountered while performing OSNR monitoring in long-haul transmission systems is that the nonlinear distortions are often incorrectly treated as noise by most OSNR monitoring techniques. In this context, Caballero et al. Have demonstrated the use of artificial neural networks for the joint monitoring of linear and nonlinear signal-to-noise ratio. Their approach is based on the fact that the nonlinear interference is power dependent and therefore it causes the normal and tangential noise components to differ from one ring to another in a constellation diagram. This figure shows the dependence of normal and tangential components of the noise on the nonlinear signal-to-noise ratio. Similarly, they have shown that the amplitude noise covariance is sensitive to nonlinear signal-to-noise ratio. In their technique, the normal and tangential components of various constellation rings and amplitude noise covariance along with number of WDM channels and accumulated chromatic dispersion are used as input features of an artificial neural network. And the trained artificial neural network is then used for predicting linear and nonlinear signal to noise ratio. Their results have shown that this ANN-based technique can jointly estimate linear and nonlinear signal-to-noise ratio with standard deviation errors of less than 0.23 dB. The emergence of software-defined networks with their inherent programmability feature and access to large amount of monitor data offer unprecedented opportunities for the application of machine learning techniques in order to realize self-aware, self-managing, and self-healing future optical communication networks. Machine learning-based data analytics can enable several useful functionalities in future optical networks. For example, machine learning-based techniques can be used to predict the physical conditions of various network elements. This in turn can help in the realization of proactive fault detection and preventive maintenance in optical networks. Similarly, machine learning-based techniques can be used to predict data traffic patterns in optical networks. This can be helpful in adaptive resources allocation, for example, routing, modulation format, and spectral assignments in optical networks. The conventional fault detection methods in optical networks are passive in nature. In this case, some fixed threshold limits are set by the system engineers, and alarms are triggered to indicate malfunctions once those limits are surpassed. This approach results in loss of large amount of data during the network recovery process once a failure happens. In contrast, machine learning based Proactive fault detection mechanisms perform dynamic data-driven operations. In this case, operational data collected by various network monitors is exploited. This data may include parameters such as optical powers at various nodes, current drawn and power consumption of various devices, temperatures of various devices, etc. Next, machine learning based data analytics is performed to uncover the hidden relationships between the values of these parameters and the occurrence of various failure events. Machine learning based proactive fault management can enable several useful tasks in optical networks. For example, fault detection, fault classification, which is basically the categorization of failures as hard or soft failures, fault localization, fault identification and root cause analysis, and fault recovery. Rafiq et al. Have demonstrated machine learning based proactive fault detection and root cause analysis in optical networks. Their approach makes use of artificial neural network and clustering algorithms. In the two-stage framework proposed by them, optical powers are monitored at various network nodes, and also the node's local features such as gain, optical power, temperature, and current drawn are monitored. In the first stage, an artificial neural network is used to detect the faults by identifying the power abnormalities. The faulty node is then localized by network topology mapping. In the second stage, the faulty node's local features, which may also be interdependent, are further analyzed by shape-based clustering algorithm to identify the actual root causes of the faults. The failures in optical networks can be categorized into two types: hard failures, which are the ones which cause major signal disruptions, and the soft failures, which are not disruptive but they degrade the system performance slowly and slightly. Recently, Shariati et al. Have demonstrated the use of machine learning techniques for soft failure detection and identification in optical networks. The soft failures considered in their work are the filter shift and filter tightening. In their approach, they exploit the features of optical spectrum for soft failure detection. These features are extracted by using a features extractor module. The features considered in their work are the bandwidth of the optical spectrum, the center frequency, the symmetry, the edges of the optical spectrum, which are computed by using the derivatives, and also various cutoff frequencies. In the first stage, they make use of a decision tree based classifier to classify the optical spectrum as either normal or affected by laser drift or affected by filter failures. Now, if the first classifier detects a filter failure, then in the second stage, they make use of an SVM or decision tree based classifier to further predict filter shift or filter tightening. The results demonstrate that both SVM-based classifier and decision tree-based classifier can detect filter shift and filter tightening with good accuracies. The performance of SVM-based classifier is relatively better than that of decision tree-based classifier. For SVM-based classifier, the filter shift detection accuracy is greater than 96% and filter tightening accuracy is greater than 80%. Another area where machine learning techniques have been applied successfully is software-defined networking. In software-defined networks, we can capture abundant data by accessing the monitors spanning the whole optical network. The captured data may include parameters of the transmitter and also various network elements. These parameters may include, for example, launched power, EDFA's input and output powers, EDFA's gains, EDFA's noise figures, etc. Next, machine learning based data analytics can be applied on the captured data to enable various useful functionalities in software-defined networks. For example, network planning and performance prediction and adaptive resources allocation, such as routing, modulation format, and spectrum assignment with the objective to maximize the link capacity. Recently, in this paper, we demonstrated machine learning assisted light path provisioning and optical network planning in software-defined networks. In this work, we implemented a network scale configuration and monitoring database. This database stores network configuration information from SDN controller, and it also stores various parameters of the network, such as transmitter, receiver, and optical paths parameters. Next, an artificial neural network is used to learn the hidden relationships between various network parameters, such as launched power, EDF phase input and output powers, EDF phase gains and noise figures, and the OSNRs of the established light paths. After training, this ANN is able to predict the OSNRs of the unestablished light paths. Our results demonstrate that this ANN-based technique is able to predict the OSNRs of the unestablished light paths with reasonably good accuracy. The estimated OSNRs are then used for adaptive light path provisioning in software-defined networks. We demonstrated field trials over NDFIS facility in United Kingdom. Similarly, in this paper, machine learning-based techniques such as k-nearest neighbor and random forest algorithms are used for predicting QoT of the unestablished light paths. In their work, network parameters such as number of links, total length, longest link length, traffic volume, and modulation format are used as input features to a machine learning based classifier. And this classifier then predicts whether bit error rate of the candidate light path meets the required system threshold or not. In their analysis, they have shown that three parameters, that is total length, traffic volume, and modulation format, are the most critical for accurately predicting the QoT of the unestablished light paths. Recently, Chen et al. Have demonstrated the use of a reinforcement learning technique called Q-network for joint routing, modulation format, and spectrum assignment provisioning in software-defined networks. Unlike supervised learning, the Q-network is able to self-learn best RMSA actions under different network states and variable traffic demands based on the feedback obtained from the network for the RMSA actions taken in those conditions. The optimal RMSA actions in this case are the ones which reduce request blocking probability. Their results have shown that as compared to conventional shortest path routing and first fit spectrum assignment approach, the Q-network based routing, modulation format, and spectrum assignment approach reduces the request blocking probability by 4 times.
All right, lastly, I want to spend some time to talk about some observations and trends of how we are trying to apply machine learning techniques into our community of optical communications and networks. Now, the first thing is you will see there's a lot of papers talking about applying a lot of machine learning techniques, but in fact, a lot of them actually you can also say it is standard statistical signal processing. So that is because in reality, a lot of the machine learning techniques are actually based on statistics and probability. For example, like stuff like hidden Markov chains, regression, linear regression. We talk about PCA just now. Common filtering, Bayesian analysis. So these sort of stuff are actually belongs to standard statistical signal processing, which also is part of the overall machine learning literature. So sometimes we actually know these stuff as someone who is in the more signal processing sort of background. Okay, so therefore, some of the machine learning applications in optical communications, they are actually based on stuff that we kind of already know. All right. Another thing, it's you see a lot of these algorithms, a lot of these research work, they try to apply machine learning to a problem that you cannot really analytically characterize. Okay, and also there are times when we actually spend a lot of effort to try to come up with good features to be input to learning algorithm. Okay, so in reality, especially for disciplines like us, optical communications, which are based on solid physics, a lot of times it is the task is completed by a joint effort between machines and humans. Now, I'll take OSNR monitoring as an example. Um, so we talk about a case where you can take the whole eye diagram and take it as an image input, okay? Put it in a deep neural net, you'll be able to monitor the OSNR. Now, if you know a bit more about the underlying physics of the problem, you will know that maybe you should just look at the center of the pulse and then extract the empirical distribution. Then in this case, you put it in a more simple neural network. You should be able to monitor the OSNR as well. Now, in the extreme case, if you know enough about statistics, okay, you can actually derive the probability distribution of these pulse centers, okay, and then it's a non-central chi-square distribution, and then you can fit fit the parameters of the distribution to maximize the likelihood of what you see. So in that case, you can also estimate the OSNR. Okay, so this represents a whole spectrum of how much humans can help and how much machine can help. Okay, so in our disciplines, this trade-off is important because in our disciplines we are seldom 100% clueless about the underlying physics of our problem. Okay, so our discipline is based on solid foundation of physics. So therefore, it is always good to try to know as much as possible based on our analytical understanding, and then for the rest of the problem, you might be able to ask machine learning for help. Okay, but it is always good to throw in as much physics into a problem as possible. Now, whatever I said just now, for some disciplines it might not be true because for some cases, machine learning has shown that our conventional wisdom is wrong. So therefore, it might not be 100% true, but then for what we have seen up to now, it seems like it is always beneficial to throw more physics into the problem before we ask machine learning to take care of the rest. Also, what is the hype that drive deep learning everywhere? So why does everyone talk about deep learning these few years? Now, we want to talk about this because this gives us a bigger perspective. Now, the reason why partly is because of this what we call image recognition challenge back in 2012. In that year, there is a new convolutional neural network that substantially outperformed others, and that actually sort of drives up the interest in deep learning again. Okay, so this is a graph showing the classification errors of those images as a function of time. Okay, so you can see that at 2012 the classification error significantly goes down, and it continues to improve more and more. Now, what I want to highlight here is that this is development of the machine learning computer science community, and so what they are really doing is, before 2012 they are just using more traditional shadow neural net, right? And then 2012 we have 8 layers, and then year after year they have more and more complex, more layers, right, in the deep neural networks. Right? So in a way, basically there's a competition of having more and more complex neural nets, and then they will be able to perform better and better. So in fact, in this day and age, for these sort of contests, the neural networks can actually beat human performance. Okay, so in their community, it is like it's a contest of how complex your neural network can get. Okay, so now, however, for our discipline, we are basically consumers of these machine learning advances. The question that we want to highlight is, in our disciplines, are there any problems that are so complex that we need more than 10 layers of neural nets? Now, this question is relevant because if our discipline doesn't have these sort of complex problems, then the machine learning hype might not be that relevant to our community. Okay, so if you look at the proposed machine learning techniques in our community up to now, I don't think there are any neural nets that is beyond 10 layers. Okay, so it might be true that whatever our problem we are dealing with, we actually don't need, anything that is that is so complex that is derived in the past 5 or 6 years. Okay, all right, and also more importantly, sometimes it's more about the data set. So what we mean is the following. So if you look at the computer science machine learning literature, so you have a lot of people, a lot of researchers trying to come up with better machine learning models. Okay, and then a lot of times they actually use standard data set for benchmarking their performance. Okay, now however, for a lot of industry applications, the actual relevant problems um, are, more on the data set itself. Okay, so a lot of the troubles, a lot of the objectives in actual problems is to get relevant data sets, uh, less about coming up with very complex machine learning models. In fact, for a lot of applications, not just communications, all other areas like medicine, healthcare, and also other areas of engineering, the important problems is actually getting the relevant data sets, and then afterwards you actually use relatively simple machine learning models. Okay, so um, so therefore, in our community, I think that it it may be harder to get relevant data sets for us to do meaningful things than coming up with overly complex machine learning models. Now, one example is to get a good data set for network operations, for your traffic modeling or for adaptive SDN sort of applications. Okay, so at this moment, there's no standard relevant data sets for people to work on. Okay, and that will continue to be a challenge because it is not easy for a real operator to take um, relevant data and then open source it and then let all of us play around with it. Okay, so this is one of the actual implementation issues when it comes to applying machine learning to an actual problem. All right, so as a summary, I think we spent some time to talk about some basics of machine learning techniques, and then we talk about 4 areas of machine learning applications in optical communication and networks. So we personally feel that our soft fault identification probably has the highest impact. So we think these sort of machine learning applications, this wave of research, I think is good in the sense that I think the basic concepts is something that we should all know, like ANN, SVM, PCA. This sort of stuff is some handy tools for any science and engineering discipline. Now, the two fundamental problems that we deal with, okay, so namely maximizing the transmission speed from one point to another, and also maximizing the information flow in a dynamic network environment, um, eventually will be somewhat benefited by machine learning, okay, if we know how to incorporate our domain knowledge um, appropriately. Now, lastly, there are plenty of online courses and codes freely available, so don't start from scratch. So the last section of our paper details some places that you can find readily available codes. Also, now, this paper is not the only paper that gives a good overview of machine learning applications in optical communication networks. Now, there are at least quite a few other also very good papers. Some of them actually focus more on the network side, and we definitely recommend you to take a look at those as well. And also, we would like to take this chance to thank one of the reviewer who actually spent a lot of effort and time to polish our paper in every single detail. So we really appreciate the dedication of that reviewer. And thank you very much.